Okay, so what we have here is a pulse motor that doesn't uses magnets. All right. So I'm gonna stop it and show you what's inside. So right, this is the timer that times the rotor, and pretty much this is what's inside. So I have a bunch of E-core ferrite placed around the periphery. What I have next is the way I wind the coil is it's looped this way, wraps, it's looped that way, and it's wrapped around the stator in opposing direction. So the fields repel each other. Good. So let me take this apart and show. Let's see. Okay. So that's the rotor. As you can see, it has the ferrite core. This is the eye. And this is the stator. All right. So those coils are wound so that their magnetic fields are opposing each other. So for example, let's say I have North Pole on the inside. North poles repelling each other. In the center core of the E core, you're gonna have North Pole, and on the outer portion of the core, you're gonna have South. So the magnetic field are looping around. And winding it like that in opposing direction reduces the inductance of the coils, which ultimately reduces the input voltage necessary to give you a required current flowing through the motor. All right, so let's put it back together. Now, I have to select the timing of the rotor. So what I'm gonna do is I have to get the best position. Let me send small amount of current. So I turn it. So that whenever I get the current, indication that the current is flowing, I look at the rotor position and I turn this. Right there. Let me go back a bit. This can be a bit time consuming, but it's worth it. Okay. After a bunch of trials, finally got the timing right for the motor. So let's start it up. As you can see, it's touching against the. Ugh. I have to retime it again. Let's see. Okay, go with that. If it's some, it's a bit crazy to just. Okay. I'm cranking up the voltage. Actually, 20 volts. I'm gonna go with 18. So you can see the frequency of the coil. Pulse frequency of the coil is approximately 332 hertz. Now this is actually measuring the current going through the coil, and I have a recovery diode, so I use the diode to prevent the back EMF from going through to the IGBT transistor. So as you can see, the current input is 0.25, but this meter isn't accurate, so you have to add about 0.2 to it. So the current input right now, it's around 0.4 volts, 0.4 amps, or 0.5 amps. While, as you can see, the current going through the coil is actually 1.8 amps. All right, why is that? So why is that? So if I look at a simplified circuit, right? So I have the power source, right? I turn the switch on. In this case, the switch is the transistor with the photo gate. So you have current flowing through the coil, right? This way. When I turn the switch off, what happened is, due to the stored magnetic field energy, due to the stored energy in the coil, due to the magnetic field, it tries to maintain that magnetic field. So it tries to maintain the current flowing through. So in that case, it starts flowing through the rectifier, or in this case, let's say a diode. I should have used a diode here. So it flows through the diode, right? So therefore you have that creates a negative resistance, so you have additional current flowing through the coil. So that's why you have excess current flowing through the coil compared to the current from the power source. But that doesn't say that this is over unity or anything like that. But it's just interesting. Now let's use this tachometer to measure the RPM. Let's see. Right now the RPM is 678. And you can also calculate the RPM based on the frequency of the coil. And with that frequency, you'll get, let's see, RPM, the RPM will be equivalent to frequency times 60 divided by the number of poles. So in that case, RPM equals, the frequency is 340 hertz approximately times 60 divided by the number of poles on the rotor is 30. So that's going to give me approximately 680, which is revolutions. That's going to give me revolutions per minute, which is close to what I measured with the tachometer. Right?